This is Lab 4 Magnetic Braking with Faraday's Law by William Brantley. So the introduction to this lab. So in this lab, we will observe and explore the interaction between the falling magnet and through the tube of aluminum foil. Then we will model this interaction computationally using glow script, and then we're going to compare our computation predictions with our observed data. So our fundamental principles are Faraday's law, the Biot-Savart law, Newton's second and third law, magnetic force on the loop, and Ohm's law. In the overview of the results in the experiment, it took 1.232 seconds to fall through, and the computational model 1.118 seconds. Assumptions, gonna disregard air resistance on the falling magnet, and then gravity and the magnetic force are the only two forces acting on the falling magnet. So our experiment, our system is going to be a magnet and aluminum tube, and then surroundings, obviously everything else. And the procedure we followed is we used a magnetometer on our phone or on my phone to find the north pole of the magnet. Then we set up a camera and recorded the 5 trials of dropping the magnet through the tube. And then we used this video footage to calculate the time it took for the magnet to fall. This is the data. So trials 1 through 5, and we have an average of 1.232. Checkpoint questions. So the first one is, why can't we use a ferrous tube? For example, a steel pipe. And a different material wouldn't react to the magnet the same way. And then the second question is, what happens to the magnet? How does this compare to a magnet falling free in space without a tube? And to that, the induced field makes the magnet fall slower compared to if it was falling in free space. So this is our computational model. So you can see we have our physical constants. We create the tube in step 1 using our data. And then we create the bar magnet. And then they have the definition of the dipole. We go here. We're doing the simulation loop, gravitational force on the magnet, and then calculating the magnetic force from the tube on the magnet. And then we're doing some computations. The ring current equals the flux divided by ring.r. And then we finally have F net equals F grav plus F magnetic, obviously. And then we apply Newton's second law. And then this is the final model, so you can see the tube, and then velocity versus time graph. So discussions, possible sources of error. Obviously, we could have human error in finding the time of the trials, and then we use the mu value we found in lab 3, so that could be incorrect. For discussion questions, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to Ohm's law, the induced current would be much greater and the time would increase. And then the last question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would lower the number of rings, so the current would be less, and it would fall faster, so time would decrease. Thank you.